All right, so we've defined this mysterious notion called NP completeness. Problems where not only can their solutions be checked in polynomial time, but a problem which is somehow general enough so that any problem where solutions can be checked in polynomial time can be translated or expressed as an example of this problem. Well, in 1972, when the notion of NP completeness was first invented, this was fairly mysterious. And like I said, it wasn't obvious that any such problem exists. But nowadays, you walk around with problems like this in your pockets because we have computers that can do nearly anything we ask them to do. So that means that predicting the output of a computer or telling if you can get a computer program to produce a certain output includes checking all sorts of things. What do I mean? Well, suppose that you were writing a solution checking program for the Hamiltonian path problem. A friend of yours has given you a particular graph that they really like. And now you're writing a program that it doesn't try to search, it's just trying to check. It takes a proposed tour of the graph in some agreed upon format, and it just makes sure that it visits each node exactly once and travels along the edges. You know in your heart that you could write such a program in your favorite programming language. It wouldn't even be that hard. You also know something else. You know that if you compiled this program, it would get broken down into simpler and simpler steps, down into machine language, little operations being done to a few bits of information in the computer's memory by the chip. And you might also know that if we think about breaking down those operations even further, they become operations on single bits, logical operations, what we call Boolean gates. Like in this diagram, x1 and x2 could be two of the input bits that describe our proposed path. And then, for instance, they get fed into this OR gate on the left. What does it do? It produces an output which is true if and only if x1 or x2, or possibly both, are true. The AND gate on the right, its output is true only if x1 and x2 are both true. And then there's a NOT gate that flips true and false. So you know that although this would be extremely tedious to do by hand, you could take your path checking program and break it all the way down into a Boolean circuit which does these operations on single bits. Finally, the circuit would output a single bit saying, yes, true, if that proposed path actually worked. What have we done? Well, we've used the fact that Boolean circuits can do computation, which is why we build computers out of them. Each one of these gates is a couple of transistors, basically. And we've taken our original question, does your friend's graph have a Hamiltonian path? And we've translated it into this question, is there a way to feed inputs into this Boolean circuit so that the output is true? Okay? So, all I'm saying here is that because Boolean circuits can compute, the general type of question, here's a Boolean circuit, is there anything I can plug into it that will make it output true, includes any solution checking program you can imagine. If the program runs in polynomial time, then the total number of these Boolean gates in the circuit is also only polynomial, which means I could hand the whole thing to you laid out as a map and ask you, hey, is there any way to make it output true? Well, this is our first NP-complete problem. It might almost be a little disappointing to you because I've really just rephrased the definition of NP. I've rephrased the question. Here's a solution checking program. Is there any way to get it to say yes, which is the same as saying, is there a solution? All we've done is change that program into a Boolean circuit. Okay, but this still gives us a starting point to translate this question into many further questions, including some that don't at first look at all like they're just running a program or simulating a computer. So, our next transformation is from circuits to a type of logical formula. We're still in Boolean world, but give me time, give me time. What I'm going to do is add a bunch of additional Boolean variables that represent the truth values, the bits being carried internally on the wires of this circuit. So for instance, that wire leading from that OR gate into that AND gate I'll call Y2, and that'll be Y1 and Y3 and so on. Well, now I'm going to take the claim that this circuit works properly, that it does what it's supposed to, and write it out as a big logical formula. So for instance, one of the parts of this claim is that Y1 is the logical AND of X1 and X2, that Y1 is true if and only if both X1 and X2 are true. Well, let me introduce you to some notation that you may or may not have seen before. These V's here are ORs, they're kind of pointy union symbols. The wedge things, the upside down V's, are ANDs, they're kind of pointy intersection symbols. And the bar stands for negation, for not. So, what does this little formula say? It says either X1 is true or Y1 is false, and either X2 is true or Y1 is false, and on top of that, either X1 is false or X2 is false or Y1 is true. That's what this says. All right, so here's a quiz for you. Check that this logical formula, which is this AND of these three ORs, is equivalent to the claim that Y1 is the AND of X1 and X2.